This is Fluid Mechanics Homework number 4, Part B. The problem statement is asking a canal is a trapezoidal cross-section such that the width of the water level in meters is WT equals 4 plus the depth over 4, where D is the depth of the water in meters. Derive an expression for the hydraulic radius as a function of depth. So, first thing we always do is draw our diagrams. So we're going to draw a diagram of this trapezoidal cross-section canal. So here's our canal. It's filled with water and it has a depth of little d. This is going to be our width bottom. And we're going to be comparing this trapezoidal canal to just like a regular circular cross-section pipe. So I'm going to draw that as well. That was horrible. So here's our circle. And this is going to have a radius of r and also a diameter of big D, which will come into play later. And as we can imagine, both of these are probably gravity fed, so we will have a difference in our z coordinates. So we're going to label this z2 and z1. And yeah, let's get into this problem. So to derive an expression for the hydraulic radius as a depth function, we're going to be using the frictional work equation here. So we have our big F is equal to F L over D V squared over 2. And to identify the small f, we're going to be using the Churchill equation. And from the Churchill equation, we need to use the Reynolds number. And as we can remember, the Reynolds number is equal to rho v d over mu. And now we can share this into our Bernoulli's equation. And for our Bernoulli equation, we know our injection work, so delta P over rho plus V of G delta Z plus V2 squared minus V1 squared over 2 is equal to negative of our frictional work. For this situation, this is going to be 0, this is going to be 0, and we can substitute in our f for this equation that we came up with before. So we have our G delta Z is equal to negative, substitute in, so we have small f L over D V squared over 2. So now that we have this equation, let's really think about how we can derive an expression for the hydraulic radius as a function of depth. And the way we're going to do this is we're going to remember that the shear stress along this point right here on our circular pipe is going to be equal to the shear stress found on the walls of our trapezoidal canal. So what this means is we can utilize a diameter of a circular pipe, which we already know how to work with, that represents the hydraulic diameter of our trapezoidal canal. Sorry, hydraulic radius. We get the shear stress is equal to the viscosity times some velocity with respect to some surface. We need to solve for our hydraulic radius. So we know that the width on top is going to be equal to WB plus D over 4. And so our hydraulic radius will be equal to the area over perimeter, which is equal to our bottom width of our canal plus the depth over 8 times the depth over our depth times the square root of 65 over 4 plus the bottom width. And this has to be equal to pi r squared, which is the area of our circle, over 2 pi r, which is the perimeter, which is equal to r over 2, which is equal to d over 4. And this is the relationship and expression for the hydraulic radius as a function of depth. All right, part B, part 2 of homework number 4 is asking for over a length of 200 meters, the canal's elevation drops by 10 meters. Using Churchill's equation for the Darcy friction factor, use Excel solver to determine the depth of water in the canal at a flow rate of 5 meters cubed per second. So for this part, I will be using an Excel sheet that we created in class, and I've also utilized it in a previous video in homework number 3 that used the Churchill equation in order to output a cost for various variables. But for this case, we're going to be using it to solve for a depth of our trapezoidal canal utilizing Excel solver. So let's see what variables we need to change. So we have a length of 200 meters and the canal's elevation drops by 10 meters. So our h in this case will be 10 and our L is going to be 200. And what else? We have to determine the depth of water in the canal at a flow rate of 5 meters cubed per second. So we're going to change our flow rate to a 5 here, and we're going to utilize the solver, which is found in data solver. And we're going to be changing the variable cells of our depth, which we want, and also our velocity. So solve. Okay. So that's kept our solver solution. And as we can see, the Bernoulli side of our equation is close to 0, as well as the flow, which means that the depth in this case would be an accurate calculation. So the depth of water in the canal is going to be equal to 0.8732, and that is the answer to our part B, part 2.